Okay, thank you very much for the introduction and for the invitation. So this talk is going to be about neural networks, also known as deep learning, which, as many of you know, has been most dramatic development in machine learning and AI over at least the past decade. These learning systems are nowadays routinely used for things like detecting objects in images, and for automated translation, and for speech recognition, and for beating world champions in various games, even doing certain types of art, as well as anticipated to play a key role in things like autonomous driving. There are, scientifically speaking, there are many things we don't understand about these things. This talk will focus on one aspect, namely what kind of functions neural networks can and cannot express. So just to sync what I mean by neural networks in one slide, neural networks are composed of neurons. So these are simple computational elements which, given a vector x, maps to some affine transformation of this x composed with some fixed nonlinear function. Maybe the most popular example nowadays is the ReLU function, just the max of 0 in the input. And these neurons are stacked together in layers, with the output of one neuron being the input of the next neuron. These neural networks in general can be described mathematically as follows. So you have your input, which is generally a vector in Euclidean space. You apply some affine transformation. You push it through some nonlinear function. Then you again do an affine transformation, again a nonlinear function, and so on for k times, where at the end, usually you just, the way that we will model it, you just do some affine transformation. Basically, learning neural networks is given a collection of examples of inputs and desired outputs. What people do is to take a network of this form and tweak the parameters, these matrices W and these vectors B, trying to make this thing predict well on the data, using some local search, usually a variant of gradient descent. And maybe the two most basic architectural properties of these networks is the depth of the network, the number of affine transformations we apply, or the number of layers, and the width, which is basically the maximal number of neurons in a layer, or in other words, the maximal dimension of these parameter matrices. Okay, clear so far? Okay. Now, one of the things that distinguish modern neural networks, those associated with these huge improvements on many applications, is that they tend to be very deep, much deeper than classical neural networks from the 1980s and the 1990s. So for example, maybe the network that started the deep learning craze back in 2012 was a network architecture called AlexNet, which was 8 layers, which won like a tough image recognition challenge. 2 years later, the winner was already a 19-layer network. A year after that, we already went up to 152 layers, and nowadays you can see lots of papers about networks with even 1,000 layers or more. And the very natural question is, do we really need this depth for deep learning, for getting these kinds of amazing practical results? And so first of all, empirically, the answer is very clearly yes. I mean, the kind of performances you can get with these networks is nowhere close to what you can get with shallow networks with just a few layers. And when you think about it, it's also very intuitive, because many of the difficult tasks that we apply neural networks to are naturally modeled as a pipeline. So for example, if you want to have some predictor that takes the raw pixels of an image as input and outputs what's in the image, it's kind of natural to think of a system where you first take the raw pixels, and then you do some transformation, you compute certain features, and then you use that in some predictor in order to get the output. And this is actually the way classically these systems were formed. So first, people came up with various handcrafted features, SIFT and all kinds of other things, and only then fed these to some learning algorithm resulting in a predictor that, given these features, maps it to the output. If you talk about translation, it's even more clear that you have a pipeline structure, because the natural way to do it is that you take, say, a sentence in Chinese, then you maybe parse it into individual words, then you translate them, then you put something back. And again, classically, you have an entire pipeline, some of it handcrafted, some of it learned. And the promise of deep neural networks is that you don't really need to explicitly have this pipeline anymore. Just take a big, large, deep neural network, and just let the network learn for itself how to do this pipelining. You don't really have to split the tasks yourself. But intuitively, to do that, you need some kind of depth to get this kind of pipeline behavior. OK, so but if we look at this from a more theoretical perspective, can we actually prove the depth is needed for expressing certain types of predictors? So in one sense, the answer is no. And that's been known for a long time, because we have these so-called universal approximation theorems, which tell you that take a two-layer network with just about any kind of activation. It doesn't have to be a ReLU. Anything which is non-polynomial would work. And you can approximate any function from some bounded domain to the reals to any accuracy that you want. Of course, there is a catch to this, and that's that at least the construction used to prove these things uses networks which are very, very wide, at least exponential in the dimension, which are not very useful, computationally speaking, and just storing these networks. So what if we talk about efficiently computable networks, networks which are polynomially sized? OK? Yes?
What's the notion of accuracy?
So we'll discuss it later, but it can be like the expected squared loss. In just about any reasonable metric, you can show these things hold. But again, you need huge networks. OK, so trying to crystallize the main question here, what we're going to ask here is, are there any functions in Euclidean space which are, on the one hand, expressible by neural networks of a given architecture with a certain depth and width, but if you try to even approximate them by any shallower network with depth less than h, you can't do it unless the width is huge. So for example, cases where the neural network is of size polynomial in the dimension, but if you try to approximate it with a shallow network, you would need a width which is exponential in the dimension. And following your question, the kind of approximation metric that is most natural in the context of machine learning is that we look at the expected loss with respect to some data distribution. So particularly in this talk, it'll be the square difference between the network and the target function in expectation over some distribution over Euclidean space. OK? So for this audience, this kind of question should sound familiar, because this is exactly the same type of questions that people have been asking in circuit complexity for several decades now. The motivation maybe is a bit different. So in theoretical computer science circuit complexity, it's more about, or at least the motivation was separating P and NP, and here it's different, but the actual question is the same. This is a mature field in theoretical computer science with many known results. So for instance, if we talk about Boolean circuits, where the elements are logical gates, then there are results separating any two constant depths. So give me any depth, I can give you a function, a Boolean function that you can express with that depth, but with any shallower depth, you would need exponentially large circuits. in the context of threshold circuits, which are really nothing more than neural networks where the activation is a threshold and the inputs and outputs are Boolean, we also have results. So it's well known that you can separate depth 2 and depth 3 if the weights are bounded. And moreover, we know that at some point we're going to hit some barrier, particularly the natural proofs barrier that maybe I'll explain a little bit later on. But anyway, we have a lot of existing results. Another class of circuits that people have been studying is arithmetic circuits, which again are neural networks, but where each neuron computes a sum or a product. So it's really a network that computes polynomials. And here again, we can say various things. So why can't we just take all these results and apply them in the context of neural networks, of the modern neural networks that people are using nowadays? So what I would like to, yes?
Depth 2 in the DC0 case means 2 layers of majority so threshold case, right?
Yes, yes. I mean, there's a slight semantic difference here that in our formulation, we always assume that the final layer is linear. But yes, up to this thing, yeah. OK. But what hopefully I'll be able to convince you in this talk is that modern neural networks are really a different beast than these circuits that have been well studied, because they have non-Boolean inputs and non-Boolean outputs. That's a natural way to represent the data that modern networks are using. And moreover, the activation they use are not polynomial functions. So because the inputs and outputs are non-Boolean, it's not Boolean circuits or threshold circuits. Because it's non-polynomial activations, these are not arithmetic circuits. And although it's not that these things are completely unrelated to neural networks, as we'll see, there are connections. But the playing field is really a little bit different here, and different kind of ideas and results and techniques apply. I should also say that neural networks and circuit complexity is something that has been studied in the past. There's actually an entire book about them written in the 90s. But the focus has mostly been on expressing Boolean functions. And again, here I want to talk about functions which are not Boolean, where the inputs and the outputs are real valued. And again, hopefully you'll see that things really behave a little bit different here. Any questions? OK. So in this talk, I'm not really going to talk about one particular result or even just my own results. It's mostly going to be some survey of the kind of depth separation results that people have managed to obtain in recent years in the machine learning community. It's all something that started very recently, and hopefully I'll show you some examples of the results and the techniques we use. But there are many open questions here, and I think that it's a shame that currently this work is pretty, so the communities that is doing these things is very far from the circuit complexity community in theoretical computer science, and I think there are many opportunities here to explore more connections between these two, because the questions are very similar. And there are many, many open questions here. So if you want to do circuit complexity, but tell your friends and funding agencies that you do deep learning, I think this is a good opportunity. And of course, I'd be very glad for any comments or feedback. I am not an expert in the theoretical computer science type of circuit complexity, so I'm sure I'll be also able to learn many things from you. OK, so I'm going to start with the case of separating depth 2 networks and depth 3 networks. So just to remind you, this is mathematically how depth 2 and depth 3 networks are defined. Depth 2 is really like a linear combination of individual neurons. Depth 3, you have another layer. And I'm going to start with a result which is actually pretty close to the type of stuff that's been used in threshold circuits, but with some differences which I think might be interesting. So, so this is a theorem by Amit Danieli from last year, which says that if you look at this particular function, so you have a vector that you sort of divide the coordinates to two groups, and then you take the inner product of these and push it through some kind of sinusoidal function where x and y is uniform on the unit sphere. Then on one hand, you can approximate it efficiently with a depth-3 network with polynomial size. But on the other hand, you can't approximate it with a depth-2 ReLU network unless the width is more than exponential in the dimension, as long as the weights, the size of every entry in these matrices is at most exponential in the dimension. Okay? So this result is based on a correlation technique, which has also been used in the context of threshold circuits. And I should say I'm stating this for ReLUs, but actually it's more general. You can show it for other activations, and not just for this f, but anything which can't be approximated with low-degree polynomials. Yes?
So if you allow weights which are slightly larger, let's say, not d bits, but rather d squared bits, does it still hold?
No, and we'll get to that. At least not with this technique. So just to quickly go over the proof idea, so it's based on some kind of harmonic analysis over the unit sphere. So the idea is that if you look at this function that we defined, and you look at the function that a single neuron computes, which you can write in this form, then these functions are almost orthogonal to each other. The intuition is that a single neuron, what it does is that it takes the input and always projects it in some fixed direction. And on the other hand, this function, it takes part of the input x and then projects it along some random direction defined by y. And recall that y is chosen uniformly from the unit sphere. So because they are almost orthogonal, it means that unless you have many, many, many neurons, or you put a huge weight on at least some of the neurons, the function that you're trying to approximate and a depth-2 network, which is just a linear combination of neurons, they'll be almost orthogonal, and you won't be able to do the approximation. Now, as I said, this is not a altogether new technique, so similar ideas have been used in the context of threshold circuits. But already here you can see one maybe small difference is that the separation is stronger. So in the context of threshold circuit, the separation is up to a width exponential in the dimension. Here it's exponential in d log d. And this is not just an artifact, because with Boolean functions, you really don't need more than 2 to the d width to express them with a depth-2 network. Does anyone have any idea why? OK, the reason is that a Boolean function is always expressible by a truth table of size 2 to the d. So I can always memorize a Boolean function by using 2 to the d neurons and just connecting them together. So this already tells you that the fact that we are working in Euclidean space as opposed to Boolean space gives you something a little bit different. OK, but now let's move on to more different techniques. So the result I just discussed assumes that the weights are not too large. But is this really necessary? So if we allow arbitrarily large weights, can we really express everything with a small depth-2 network? Not very likely. In the context of threshold circuits, proving that you can drop the weight restriction, that's been an open question for over 30 years. What I'm going to show you next is that we can indeed show a result separating depth-2 and depth-3 without any weight restrictions whatsoever, but using a different technique and in Euclidean domains, not in Boolean domains. So this is based on a paper of mine from 2 years ago together with Ronen Eldan. So what we show is that there exists some function and some distribution which is epsilon approximable with polynomial size depth-3 network, but any two-layer network you won't be able to approximate unless the width is exponential in the dimension. And this works for just about any activation function you might care about. Basically, it needs to be measurable, and increase only polynomially. Okay, so the proof idea is as follows. So the construction uses a radial function. Just a function that, so f of x depends just on the norm of the input. It's very easy to approximate these things with a depth-free network because you just use the first layer to approximate the norm squared of the input. That's pretty easy. And then the second layer, you just need to approximate this univariate function g, which again is simple because it's in one dimension. But the argument is that with two layers, radial functions are difficult to approximate. And the intuition is that, again, a two-layer network is just a linear combination of neurons which geometrically look like this. So if I'm thinking of a radial function like x maps to norm of x squared, it's kind of a function that is curved in all directions, in d dimensions. And you need to capture it with functions which are curved only in one fixed direction, no matter which activation you're using. So intuitively, if you want to capture something curved in many dimensions, you would need many, many functions of this form, a linear combination of many such functions, in order to approximate them. OK, this is the intuition, but of course, it's not a proof. The actual proof uses a Fourier transform on Euclidean space. Don't really need to understand the details. It's basically a way to represent the function in a different space as some weighted combinations of sines and cosines. And the proof starts by starting with the thing that we want to lower bound. Okay, so we have some network n of x, and we want to show that this thing is lower bounded by something if it's a two-layer network. We assume that the input is sampled from some distribution with a density phi squared, y squared you'll see shortly. And then we basically want to re-express this quantity in the Fourier domain. Okay, so we start with this. We can write it as the integral of the difference squared. We do some algebraic manipulations. We push the phi inside the square. Then it's well known that the integral of a function squared equals to the integral of the Fourier transform squared. So you do that. You can decompose the transform in this way. It's not that crucial. The bottom line is that eventually you end up with something that looks like this. So it's like a linear combination of functions which are a projection of the input along some direction wi, convolved with something that depends on your data distribution. Now let's try to understand geometrically what this thing is. So I claim that when you look at two-layer networks, the structure of the network in the Fourier domain has a very particular structure. So if we look at the transform of a single neuron parameterized by a vector wi, so in the Fourier domain, it's going to look like this. And this is in the case where the distribution is Gaussian. Okay? So most of the mass is going to be concentrated along a tube in the direction corresponding to this wi. How it behaves along this direction is something complicated depending on the activation. But in all the directions orthogonal to that principal direction, you have a Gaussian decay of the mass. And a depth-2 network is basically a linear combination of these things. On the other hand, a radial function, the Fourier transform, is also radial. So it would look something like this. And the intuition is that if we have a lot of such functions which are thin, with most of the mass concentrated in some small subset of the space, it would be very difficult to approximate this kind of fat radial function unless you have exponentially many functions of this form. Okay? So it should be intuitively obvious that it's hard to approximate this function using this function, but even that we don't know how to do. So we need to add a tweak here. So the idea is that this kind of structure holds because, with this Gaussian decay, is because I use the Gaussian distribution. But nobody said I have to use a Gaussian. So in particular, what we do is that we engineer a different distribution so that if you look at the Fourier transform of its square root, it's not just that most of the mass is in a certain tube, but actually all of the mass is in a tube. So if I take a linear combination of neurons with this distribution and look at the Fourier transform, you get something like this. So you get some mass along narrow tubes, but absolutely zero outside. And then it's a simple volume argument to say that such kind of a thing cannot possibly approximate a function which is really non-zero on all of this space, because this thing is non-zero almost everywhere. Sorry, this thing is zero almost everywhere in high dimensions. Okay, again, unless I have exponentially many neurons. Is the general idea clear?
So the statement could still be true for Gaussians, it's just that the proof is not.
Yes, I mean, I would love to be able to prove this for a Gaussian. I'm sure it's true, but we just don't know how to do it. I mean, it might also be interesting because the distribution we need to use is pretty synthetic. So this is actually the density. It's some kind of function using Bessel functions of the first kind. And the function itself we use has this kind of structure. So it's basically a superposition of indicators of rings of various intervals. We basically need this structure to ensure that the Fourier transform, the function will be sufficiently fat, as I said earlier. Anyway, there are all kinds of technical details, but this is the general idea.
To follow up on Vinod's question,
yes.
Still, I guess, maybe hope that even if the tails decay, that you could decompose it into these kinds of tubes, or approximately in some sense. Is that
yeah, so the problem is that we're in a setting where I'm not restricting the size of the weights, as I said earlier, which means that I can boost this up and make it as large as I want. So even though you have exponential decay, pick any point, I can make this thing at least 1 or 10 or whatever. So in order to get this kind of weight-independent result, we need to use this kind of distribution. OK. Any other questions? OK. OK, so far I talked about separating depth 2 and depth 3 in terms of dimension. It's very natural to ask, what about higher depths? What about these neural networks with 100 or 1,000 layers? And as of today, this is an open question. We don't know how to show separations in terms of dimensions for any higher depth. In our defense, I should say that the same situation also holds in threshold circuits. But there, at least we understand that there is some barrier that prevents us from proving much higher depth separations. In the context of neural networks, I have no idea. And even though it's very difficult in the context of threshold circuits, it doesn't rule out the possibility of a simple construction for the kind of neural networks I'm talking about, because these results hardness results are in the context of Boolean functions. Maybe when you move to Euclidean space, you can somehow utilize something and get something that works for higher depths. OK, but that doesn't mean that all is lost. We can still show some higher, actually several higher depth separations. Only it's not going to be in terms of the dimension, but in terms of various other quantities. Some of them don't even make much sense in the Boolean world, but they do make sense in the Euclidean world. So I'll start maybe with one very simple and I think elegant construction due to Matus Tilgarsky, which says the following. So I can provide you with a family of functions, just mapping the unit interval to itself, such that for any k, phi of k is expressible by a depth k constant width network, that with any shallower, much shallower network, a little o of k over log k, you can't approximate it with a network even if it's polynomially wide. OK? And again, I'm stating it for the ReLU, but you can also state it for other activations. And the idea is extremely simple. So this is phi 1. It's a function that I can very easily express with ReLU. So these square brackets are shorthand for ReLU, so maximum of 2x and 0, and this is max of 4x minus 2 and 0. And this network has a property that if I now compose it with itself, I now get 2 bumps instead of 1 bump. If I compose it again, I now get 4 bumps and then 8 bumps. And I just get this zigzag function where the number of zigzags increases exponentially in k. So on one hand, expressing phi of k, this composition of k functions, I can easily do with depth k and constant width. But it's not hard to show that if I try to do it with a much shallower network, I won't be able to do it because it has so many zigzags. So phi k is composed of 2 to the k plus 1 linear segments. So any piecewise linear function with much fewer segments won't be able to even approximate it. On the other hand, we can give upper bounds on how many linear pieces a ReLU network of a given depth and width can express. And you do the math, and you can show that you just can't get so many segments with a shallow network. OK? And again, this holds for any k, which can be arbitrarily large. Another kind of direction is to look at separations. So this was separation in terms of some parameter k. You can also talk about separations in terms of the accuracy, in terms of the parameter epsilon in which you want to do the approximation. So this is a theorem together with my student Itai Safran from 2 years ago. So you can show that for a pretty large family of, yes, sorry.
So this sounds like a great separation, right?
Yeah, that's what
except so the trouble, so the reason it's not so
This
good
one?
is, yes.
Mm-hmm.
The reason it's not so good is because the complexity of the function grows with k, right? Ideally, you would want one function where you can.
Yes, I mean we'll talk about it later, but this function has some handicaps if you try to think about a natural function that that you want to use to do depth separations. But you know, maybe hold this question a few more slides because I'm going to return to this issue. Okay. Okay, so in terms of accuracy, what you can show is that for a pretty large family of twice differentiable functions on the unit cube, including, for instance, something very simple like x maps to x squared in 1 dimension, maybe just think of this function, then on one hand, you can epsilon approximate it with polylog depth and width, polylog in 1 over epsilon. But on the other hand, you can't approximate it to an accuracy epsilon with constant depth unless your size is exponentially larger, so polynomial in 1 over epsilon. I should also say that more or less at the same time, there were some independent results by Rotsky and Yang and Srikant that used more or less the same ideas. And the proof idea is, again, pretty simple. So first, in terms of the upper bound, how can we compute x maps to x squared with a polylog sized network? So the idea is that you use variants of this zigzag function I talked about earlier to extract bits. Okay, so a cousin of this function is a function that looks like this, which is 1 where the ith bit is 1 and 0 otherwise. So with log 1 over epsilon depth, you can extract the bits. Then you get x as a bit vector. And now you just do this long multiplication, the type you do in grade school. And you can compute the bits of x squared. And then again, you convert it back to the reals. And you can do it with logarithmic depth and width. On the other hand, the lower bound, the fact that you can't do it with a shallow network, this is just based on the fact that x squared is a curved, strongly convex function, and it's hard to approximate it very accurately with a piecewise linear function. So if you're using a ReLU network, it's always a piecewise linear function, so you necessarily will need many segments to approximate it very well. You could do the math, it's not too complicated, but if you want to epsilon approximate this thing with a shallow ReLU network, you really need at least polynomial in 1/epsilon neurons in order to do that. And this is in one dimension, but you can generalize it to higher dimensions. And again, not just to x squared, but any function which has some curvature along some direction at some point. It's the same, but it's the same basic idea. Any questions about this? OK. OK, so now maybe returning to what you asked about. So far, I mean, I showed you various depth separations using some kind of function. I didn't really care too much if it's natural, not natural. But in the context of machine learning, this issue of expressiveness is really just 1/3 of the picture. Because when we do machine learning, we're also interested in things like the statistical error. So we want to be able to learn these functions with a small data sample. And there's also the issue of optimization error, that we want that the kind of algorithms that we use, such as gradient descent, will be able to learn these kinds of functions. And actually, when you think about it, none of the examples I showed you so far really has this property, especially in terms of the optimization error. So they all have the same structure, that you start with some input, you do like an inner product or a norm or something like that, and then you compose it with a function which is very highly oscillating. Still a Lipschitz constant that is polynomial in the dimension, but definitely not a constant. And unfortunately, it can be shown that gradient descent methods are very vulnerable to these kinds of functions. They find such functions, in general, pretty hard to learn. So it's interesting to show depth separations, but what would be even more interesting is to show these results for functions which are natural, that I can actually expect to learn with gradient-based methods. It is possible to show some results along these lines. So maybe the first example is if you just take the function which is the indicator of an L2 ball. So again, this is from a paper of mine together with Itai Safran. So we showed that for this particular function, you get a separation of depth 3 and depth 2. It's a little bit different than what we've seen before. So here, you can approximate it with a depth-free polynomial wide network. And you can't approximate it beyond a certain accuracy, which depends on the dimension, if you talk about a depth-2 network. And the proof is really some kind of reduction from the construction I showed you earlier with these combination of rings. So the idea is that if you can approximate an indicator of a unit ball well with respect to any distribution, then you can also approximate this function with respect to any distribution, contradicting the previous result. Now, the nice thing about the indicator of a unit ball is that it is a simple function that we have a hope to learn, and you can actually see this experimentally. So if we just take a sample of data points labeled according to whether they're inside or outside the unit ball, so you can run experiments, you can train networks. And what we saw very clearly is that so first you can train a 3-layer network, which achieves a certain error. But if you now try to match it with a 2-layer network, it's very difficult to do. And it's very difficult even if you make the width much larger. So here it's a 3-layer width 100 network, this blue line. And this is when it's a 2-layer width 100. You increase it to 200, 400. At some point, it doesn't really budge anymore. This really seems to be a case where the expressiveness of 2-layer networks are not sufficient to capture L2 balls, even though we can efficiently learn them with deeper networks experimentally. You can also give some other examples of this kind. So you can talk about functions. So we have another result which talks about a function of the L1 ball. Particularly look at x maps to the one norm of x minus 1 composed with a ReLU. So graphically, it looks like this. It's 0 inside the L1 ball and increases linearly outside it. And again, you can show a certain kind of depth separation that for depth-free small width network, you can express it. And with depth 2, you can't express it unless your width is at least something like 1 over epsilon or x to the d, whatever is smaller. The proof intuition here is not by reduction. It's more like a direct geometric argument. So the intuition is this is a function that breaks along every facet of the L1 ball. It goes from constant to linearly increasing. And in d dimensions, you have 2 to the d facets. On the other hand, if you want to approximate it with some linear combination of ReLU neurons, a linear combination of things which look this way, you can show that essentially you must have some ReLU neuron breaking close to every one of these facets. And because there are so many of them in high dimensions, it gives you some kind of lower bound. I should say that this bound can probably be greatly improved. I mean, we can only show that it has to be at least width of 1 over epsilon. I'm pretty sure that the right answer is x to the d, but currently we don't know how to prove it. Any questions about this? OK. And again, for this function as well, you can do experiments, and you can really see this difference between 2 layers and 3 layers. Yes?
The experiments, if you train it, will it do a good job on your test set and then just not, like for the 2 layers?
Yes. I think this is the training error, but the test error is exactly the same.
So it's not like a
Yeah, it's not a generalization issue or something like that. Yeah.
Do you have any of these simple kinds of experiments for other depth separate? I mean, instead of 2 versus 3, do you have any conjectures for 3 versus 4? Or is that
Unfortunately, no, because we don't have a good candidate. So first of all, we don't have a function we know that separates depth 3 and depth 4 in terms of the dimension. We have these functions separating in terms of the accuracy and things like that, but they're pretty crazy in the sense that gradient descent will never work on them. They're very close to parities and all kinds of...
But certainly, like for the depth 2 versus depth 3 for the L2 ball, there's some sort of intuition there at play in your examples about things that depth 3 can accomplish really easily in terms of looking at the norm, but depth 2 can't do the way that it's set up with the linear output layer. Is there any sort of conjecture along those lines for what is something, I mean, even if it's hard to show it rigorously,
Yeah.
is there any such conjecture? Or is it
Yeah, so I mean, there are conjectures about functions that seem to require at least a certain depth. You take some norm, you apply some univariate function, then you take this, compute the norm of that. You again do, you do some composition of these functions. But currently, we don't know how to prove that these things separate anything. OK. OK, and I should say what I talked about here is just some survey of some directions that people have been working on, but it's a very active field nowadays and lots of interesting work in all kinds of other directions. So just to give some examples, there's been some interesting work by people at the Hebrew University looking at arithmetic-style circuits, but using it to study all kinds of architectural properties of modern neural networks, like the effects of convolutions and pooling and things like that. There are also a lot of works where they do depth separations, but you don't look at directly the approximation error, but at other things. So it can be the number of linear segments that you can compute, or how distorted, how much distortion is in the mapping from the input to the output, or Betty numbers of manifolds, and all kinds of other things. Also works trying to understand properties of various realistic architectures, not so much through lower bounds, but just showing how upper bounds are different for different depths. Also works actually at MIT, so people at Tommaso Poggio's group that has been working on these things. And anyway, I just want to say that by no means I surveyed everything that has been done. And so just to summarize, kind of the take-home message that I hope I was able to convey is that these are questions which are very, very similar to circuit complexity. So I think they should be interesting to circuit complexity people, but it's really not just the same old circuits. They have a different structure, it's a different playing field, different techniques apply, different ideas, things which seem impossibly hard in threshold circuits are possible in these kinds of neural networks. And I think these are nice questions to think about. And again, as far as I know, currently there is very little study of the connections between the two fields. So maybe I'll just end with some open questions that might be worth to think about. So one very natural question is, can we get depth separations beyond 3 with respect to the dimension? Alternatively, maybe you can show the same kind of barriers that are known in the Boolean world. So in the Boolean world, we have, for instance, this natural proof barrier that tells us that if we try to separate networks using any kind of property that, roughly speaking, separates not just a network from deeper networks, but from a network from random functions, and it's some property that you can evaluate giving the truth table of your Boolean function, then no proof along these lines would work. But here, these are not Boolean functions. These are real-valued functions. I'm not even sure how to define the necessary framework in order to show this kind of result here. But anyway, showing a barrier for these neural networks, I think, would be a very interesting result. Separations where you don't use very highly oscillating functions, which are very hard for gradient-based methods, I think would be very interesting. Maybe we can start just by thinking about separations for any kind of Lipschitz functions, where the Lipschitz parameter is really a constant, not depending on the dimension. Can we use more circuit complexity techniques to understand neural networks? Maybe vice versa. I don't know. Maybe the Fourier stuff could be useful for something in arithmetic or Boolean circuits. I really don't know. Another thing I think is interesting to think about is, so currently I have some candidates for functions which would be hard to express with deeper networks, but these are all very weird functions that I don't think that gradient descent will be able to tackle. So is there actually any function or even a reasonable candidate of a function that is both requires provable depth, and not just depth 4 or 5, but like 100, but still plausibly would be learned with gradient-based methods? And finally, in this talk, I focused on depth, but there are many other architectural choices that affect the expressiveness of neural networks. So I mostly focused on very simple feed-forward neural networks, but real-world networks often have additional stuff. They have some convolutional layers, or they do pooling, or they have recurrences where the output of a neuron goes back to itself, and then you endow the network with memory. You can have skip connection, where one layer connects not to the next layer, but somewhere further up. And for most of these questions, most of these directions, it's really wide open in terms of formal results. So I think I'll stop here and take your questions. Thank you very much.
Shed any light on what the 100 layers are doing with kittens?
Yes. So actually, my own conjecture is that for kittens, you don't really need a 100-layer network. So I actually suspect that this might, in a sense, there isn't such a function. I think you can actually do this with a much shallower network, and you need the depth for optimization. It somehow makes the training easier. I have no way to prove it. Maybe one argument why this is true is that if we look at the human brain, we can, given an image of a cat, we can detect it's a cat in less than a second. But an individual neuron in our brain is not that fast. It fires at a rate of maybe like once every 100 milliseconds. So roughly speaking, the network that we use to recognize cats can't be much more than 10 layers deep. Now, of course, our neurons are not even remotely close to the neurons that these artificial neural networks use, but I don't know, maybe it says something.
I heard an interesting talk a couple of years ago by someone who studies physical synapses.
Mm-hmm.
And apparently there are things going on in synapses at megahertz rates.
Mm-hmm.
What this has
Right.
to do with what the brain can compute is completely unclear.
I agree. Yeah, I mean,
Higher frequency
we-
than the basic 10 hertz or 100 hertz cycle.
I agree. I mean, we don't even really understand how a single neuron operates, and there could be things that are at much higher frequencies. But you know, if these networks really use these low frequency firings, then it seems that they can't be too deep. But yeah, who knows? Yeah.
Sort of just a vague, maybe you can comment vaguely, but when these things are implemented, they're presumably implemented in finite precision. They sort of are Boolean circuits to some degree, maybe let some constant factor blow up and how much. So yeah, I don't know, what is that?
Yeah, I mean, it's true that in some sense computers eventually use bits and things are Boolean, but somehow I don't think in general for networks it plays such a big role. So I don't think if you take a given standard network and double the precision, things would behave very differently. It seems to me that the right representation here is real valued. And again, I think it's interesting that it leads to different kinds of questions and results than in the Boolean world. Yeah?
Yes, so you were mentioning how many of the results transcend which activation function you use.
Yes.
So I was wondering if you looked into maybe different types of activation functions where they're not like the standard ones, but like imagine taking some complex circuit, approximating it with a polynomial, doing convolution with a different activation function, and then using that as a module,
Yeah.
overall. Does that change? Like, you thought about that? Does that change anything?
Yeah, so in the results I talked about, it doesn't matter too much, but definitely in practice, the choice of activation helps. And I think this is exactly one of these additional properties besides depth and width that we should be able to understand, how the choice of activation affects the expressiveness of these networks. But yeah, currently we don't know to say much.
Is there any result other than fully connected network, even for the depth 2 and 3 case?
So what, for example?
I don't know, like these less nets, but just 2 depths and kind of like that. I mean, other than fit-forward structure.
Mm-hmm.
For depth 2 and 3.
I mean, so for resonance, I mean, you can import some of these results. I mean, the fact that you can express something with a depth-free feed-forward network means that you can also express it with a depth-free ResNet. And depth to ResNet, it won't really help you much. But this is just, like importing results for one architecture to another architecture. What I think would be interesting is to show some kind of separation specifically for ResNets that you cannot get by considering feed-forward networks. But again, I don't have a good example for this. I mean, most of these things are pretty wide open.
For ResNets, the intuition is that it's only to help learning but not expressibility.
Yeah, I mean, that's their claim to fame. But it could be that they also do something in terms of the expressiveness. But I don't know. I haven't thought about it very carefully, to be honest. Yes?
Has been any effort in terms of the experimental part of this? So, for example, trying to have an adversary and two neural networks, and this adversary is creating functions that could be learned by a bigger neural network than a smaller one and trying to figure out which will these functions actually be in an experimental setting.
So are you referring to things like GANs or?
I'm actually referring to the search of the functions
Mhm.
that might give us
Oh, I see. No, not that I know of. The point is that it's not too difficult to come up with conjectures. I mean, I can give functions which I think can only be expressed with a depth 4 network, not with a depth 3. The issue is that I have no idea how to prove it. But yeah, candidates, it's possible to come up with.
But
Yeah.
one can test out, right? One can run sort of gradient descent, variance of gradient descent on this conjecture.
Yes, you could, but the problem is that if it fails, it's hard to know if it's because you can't express it or just you didn't find the.
I still claim it's a win-win result, right? So either there is a real lower bound,
Mhm.
or there is a technique other than gradient descent that actually,
Right.
There is an algorithm other than which is a win-win.
Right.
It's coming up with candidates, but this is still a useful exercise.
I completely agree. Yeah, it's just that so respond to your question, it's just that I don't know of such works, but yeah, coming up with interesting and natural candidates, not just synthetic stuff, I think would be interesting. It's just that when you just look at it empirically, it's hard to prove whether it's approximation issues or generalization issues or optimization issues. It's hard to disentangle it. But
Going once, twice, 3 times, I guess.
I guess I'll follow up with on my previous question. So maybe is there any work on trying to choose theorem provers with these things?
yeah, of what?
Theorem provers or
Mm.
yeah, so very good. You have a good model of this and you search theorem prover, searching. Yeah, I mean I guess that's.
So looking for a proof that you can't approximate it with a certain, that would be fascinating, but again, I don't know how to do that.
For 2 examples, 5 or 6.
Well, but for 2 examples, the problem is that if you look at 2 examples, you can express anything you want with a constant size network with two examples. The whole difficulty is when you talk about many examples or some continuous domain. But I don't know, maybe you can still study how it scales with the number of examples. But in any case, I'm not familiar with work along these lines, but it sounds interesting.
Great open question for you.